Now in the previous lecture we have seen the derivation, and in that derivation we have seen the pressure exerted on a gas, and from that pressure exerted on a gas we have derived the expression for pressure exerted by the gas. That pressure P is equal to 1 by 3 N small m V bar square upon capital V. In that N is the number of gas molecule, small m is the mass of gas molecule, V bar square is nothing but the average velocity, that is RMS velocity of the gas molecule, and capital V is nothing but the volume of that gas molecule. That we have derived. Right? Now, what you have to study under this topic as an interpretation of temperature on kinetic theory of gases, that is how your kinetic energy of gas depends on which factor, or what is the dependence between kinetic energy of the gas and the temperature. That we are going to study under this heading. Right? Now, here interpretation of temperature on kinetic theory of gases means we want to derive the relation between kinetic energy and temperature. For that purpose, what reference we have taken? We have taken the reference of equation pressure exerted by the gas molecule. So now, pressure exerted by the gas molecule is this derivation. This equation I can write down P multiplied by this V. V I will take it for cross multiplication. P is the pressure, capital V is the volume, which is equal to 1 by 3 M into V bar square. Right? Now, what here I will do? I will multiply and divide the equation by factor as a 2. And I will write the equation in this format. What I have done? Multiplied by 2 and divide by 2. So, I will get this equation. Now, here, whatever this bracketed quantity I am getting. Now, we are going that half mv square is nothing but the kinetic energy of a gas molecule having mass m. If it is multiplied by m, meaning is this is nothing but your total kinetic energy of the gas molecule as a E. So what I say that this capital E is nothing but the total kinetic energy of a gas of which we have considering the pressure exerted is equal to here PV is equal to nothing but 2 by 3 as it is. Now, according to your ideal gas equation, what we are knowing that PV is equal to nothing but your nRT. This is your ideal gas equation. And as it is the ideal gas equation, in that ideal gas equation, your small n is nothing but as your number of moles. R is nothing but the gas constant and T is nothing but your temperature. So what I will write down? Either it is equal to nRT or I can write down capital N Kb into T, where Kb is nothing but the Boltzmann's constant and is nothing but the number of molecules. So now if I equate this equation, so this is our PV equation, this is your ideal gas equation. So if I equate equation 1 and 2, so if I equate equation 1 and 2, what I am going to write down here, 2 by 3E is equal to nothing but NKBT. Is it right? Means what I write down? Energy E is equal to 3 by 2 NKBT. Are you getting? Means in short, what I can write down? Here, kinetic energy is equal to kinetic energy of the gas molecule is equal to 3 by 2 NKBT. In that N is the number of gas molecule, KBT is the Boltzmann's constant. Means in short, what I can say that kinetic energy is directly proportional to the temperature, provided that your N and Kb are nothing but the constant. Clear? Okay, this is one equation. Second equation here I can derive as a, instead of here I can say as a, this equation, kinetic energy, this is the kinetic energy of complete gas, number of gas molecule. Instead of that I will say kinetic energy per molecule, and I will take it for division. So kinetic energy per molecule is equal to 3 by 2 kBT. This is nothing but your kinetic energy per unit molecule. Here also again it is directly proportional to temperature, because again your K is nothing but the constant. Clear? So this is to be called as interpretation of temperature on the kinetic theory of gases. And from this equation I can say that kinetic energy of the gases, gas molecule or given gas is directly proportional to the temperature, or kinetic energy per molecule is equal to nothing but 3 by 2 kBT. So in that manner we can study the interpretation. Got it? So this 2 mark question can be asked. What will be the question? Show that the kinetic energy of an gas molecule is directly proportional to the temperature. Fine? Instead of this kBT, I can use this nRT gas equation directly. So what I will say that here I can write down your, instead of this PV, I can write down as a nRT, which is equal to nothing but here 2 by 3 kinetic energy. Means what I will say that this kinetic energy, it is equal to 3 RT upon 2 is nothing but your, along with number of molecule, is nothing but your kinetic energy. Or I can say that the same equation I can write down here as your kinetic energy per mole, n is nothing but the number of mole, per mole is equal to nothing but 3 by 2 RT. This is nothing but your kinetic energy per mole. This is nothing but the kinetic energy per molecule, and this is nothing but your kinetic energy of the gas molecule. Right? So in that manner, there may be a numerical problem, so that also we can calculate with the help of these formulas. Got it? So what is the base for this? Base for this is nothing but your pressure exerted by the gas molecule. Using that, we can do the interpretation between kinetic energy and temperature. Got it? Any doubt? Clear? So this is your 2 mark question. Theoretical, MCQ as well as numerical problem. Fine? Okay. And now I am going to explain the next important theoretical topic, which is very much important for your MCQ question as well as for your very short answer question, and that topic is nothing but the degree of freedom. This degree of freedom can be written as DOF, small DOF, which is called as a degree of freedom. Now what is that? What is meaning of degree of freedom? Now let's consider, this is the gas molecule. Always we are saying the gas molecule as a spherical in shape. So this is the gas molecule, and this gas molecule is traveling along a straight line. Now this straight line is nothing but x-axis, right? So if I want to describe the position of this gas molecule, then I will require the x coordinate of that gas molecule. So if I know the x coordinate, then I can describe the position of that molecule. So by knowing the x coordinate, I can describe the position. So what I can say that degree of freedom of molecule which is traveling along a straight line is 1, because it requires only one coordinate, one x coordinate. So by considering only one x coordinate, I can able to describe the position of the particle. So for this example, I can say that degree of freedom for this situation is nothing but 1. Clear? Instead of that, suppose if I am saying that the molecule is present in the XY plane, somewhere here gas molecule is present. So if I want to describe the status of this gas molecule, what I require? Coordinate x as well as coordinate y. Means in that case, when particle is moving in the 2 dimension, this xy coordinate system is what? I can say 2-dimensional system. So when your molecule is moving in the 2-dimensional system, at that time we require 2 coordinates to describe. 2 coordinates are required to describe the position of the particle. Then in that case, I can say that degree of freedom in 2 dimension is nothing but the 2. Got it? So if straight line motion is there, degree of freedom is 1. If your molecule is moving in 2 dimension, either xy plane, xz plane or yz plane. If your particle is moving in the 2-dimensional, then it requires either x coordinate or it will require the y coordinate. So degree of freedom is said to be as a 2. So their degree of freedom is 2. Right? Instead of that, now if I am saying that your gas molecule is moving in 3 dimensions. If your gas molecule is moving in the 3 dimension. 3 dimension is what I can say that if the gas molecule is moving in the plane. So in the plane means it has 3 coordinates, x-axis, y-axis and z-axis. And here somewhere when molecule is present, so that molecule will require 3 coordinates x, y, z for its description. So at that time I can say that in this situation degree of freedom is equal to nothing but 3. Why? Because your molecule is present in the 3 dimension. So degree of freedom is 3. Got it? Now whatever this 3 example I have given along a straight line in the 2 dimension, in the 3 dimension. Here what happens? Particle is moving along a straight line. So that degree of freedoms are to be called as a translational degree of freedom. So what I say that along a straight line, translation degree of freedom is 1. In 2 dimension, translation degree of freedom is 2. And in 3 dimension, translation degree of freedom is 3. Is it right? Any doubt? So this 3 type of MCQs can come there, or there will be a 3 very short answer. Fine? So now, how we can define degree of freedom? So degree of freedom is defined as total number of coordinates which will require to describe the status of an molecule. Or instead of I can say that number of coordinates, I can say that how many independent physical quantities are required to describe the status of an molecule. That is to be called as your degree of freedom. Is it right? So degree of freedom is defined as the number of coordinates required to describe the status of that gas molecule is to be called as your degree of freedom. Fine? Okay. Now, whatever here I am talking, here I am saying molecule as a spherical molecule. So such molecule is called as a monoatomic molecule. So monoatomic molecule means I can say that hydrogen, or I can say that helium is nothing but the monoatomic molecule. So for that monoatomic molecule there is only translation degree of freedom. That is in monoatomic gas molecule either can move along a straight line or in the two-dimensional or in the three-dimensional. So its degree of freedom along straight line 1, in two-dimensional 2 and in three-dimensional 3. But if I consider a diatomic gas molecule, so diatomic gas molecule. Diatomic gas molecule, the example I can say as O2. Right? So at that time, now this gas molecule O2 will move in the three dimension. It is moving in the three dimensional means its translational degree of freedom is 3. But at the same time, that gas molecule also rotates along z axis as well as it is rotating along the y axis. Means during its rotational motion, it has a rotational degree of freedom. And this rotational degree of freedom is along y-axis and z-axis. So rotational of degree of freedom I can say as a 2. Therefore, I can say that the total degree of freedom will become as a 5. For which molecule? For diatomic molecule. Which diatomic molecule? Rigid diatomic molecule. Why? See here, your oxygen molecule. Oxygen molecule means what? O double bond O. So there are 2 oxygen molecules. Fine? So when this diatomic oxygen molecule is moving, it will move along this straight line as well as at the same time it will rotate about itself. Means it will perform rotational motion also and it will perform a translation motion also. So when it will perform translation motion, its degree of freedom is 3. And when it is performed a rotational motion, it will rotate along y-axis as well as along the z-axis. Why? Because it is moving along x-axis. So when it is moving along x-axis, it will move around the z-axis, around the y-axis. So its rotational degree of freedom is 2. And therefore, total degree of freedom is nothing but the 5. Fine? And in that particular case, now I can write down the kinetic energy of such diatomic molecule is nothing but translation kinetic energy plus rotational kinetic energy. Right? And our translation kinetic energy is what? Half mv square. Means what I am going to say here? The total kinetic energy E can be written as, first I write for translation kinetic energy. Now translation kinetic energy degree of freedom is what? 3. Means along x, y and z axis. So what I write down? Half m vx square plus half m vy square plus half m vz square. This is nothing but your total translation kinetic energy. Plus it will rotate along which axis? Z axis and y axis. Means along z axis its moment of inertia is Iz and along y axis its moment of inertia is Iy. Clear? Therefore, its rotational kinetic energy I can say as a half Iy omega y square plus half Iz omega z square. This is nothing but its rotational kinetic energy. And sum of translation kinetic energy and rotational kinetic energy is to be called as your total kinetic energy of that rigid diatomic molecule. Got it? So now here 2 type of MCQ. One is, what is the degree of freedom of rigid diatomic molecule? So rigid diatomic molecule has a degree of freedom 5. 3 degree of freedom along translation motion and 2 degree of freedom is along rotational motion. That is the first question. What is the second question? What is the total kinetic energy of rigid diatomic molecule? So total kinetic energy of a rigid diatomic molecule is equal to kinetic energy along translation motion and kinetic energy along a rotational motion. Now translation motion, molecule can move along x, y and z axis. Therefore, there are 3 terms of kinetic energy. And during rotational motion, it can rotate about z axis and y axis. Because its motion I have considered along x axis. So its rotational kinetic energy consists of 2 terms. And like that manner, the total kinetic energy term consists of 5 terms. 3 translational kinetic energy and 2 rotational kinetic energy. Got it? Fine. Then one more point is there. That is, there are non-rigid diatomic molecules. Now whenever there are non-rigid diatomic molecule, at that time what happens here? Non-rigid diatomic molecule undergoes 3 types of motion. First type of motion is translation motion. Second is it undergoes rotational motion. And third is it undergoes vibrating motion. Molecule vibrate like a oscillator. So it will oscillate along the mean position. So it has 3 types of motion. So now, how much is the total degree of freedom? Total degree of freedom is, translation degree of freedom is 3 because translation motion is along 3 axes, plus rotational degree of freedom. Rotational degree of freedom is along 2 axes. Any 2. If molecule is moving along x-axis, it will rotate along y and z axis. And plus vibrational degree of freedom is again along 2 axes. Because when it is rotating about y and z axis, means it at the same time it is vibrating along z axis and y axis. So its vibrational degree of freedom is also 2. So total degree of freedom will be coming to be 7. 3 plus 2 plus 2. So total degree of freedom for non-rigid diatomic molecule is nothing but 7. Fine. Now its kinetic energy. Its kinetic energy, first motion is translation motion. So along translation motion, it has 3 terms, half mvx square plus half mvy square plus half mvz square. These are the 3 kinetic energy terms along the rotational motion, plus half I omega y square plus half iz omega z square. These 2 kinetic energy term for the rotational motion. Plus here for vibrational motion, during vibrational motion it has a kinetic energy as well as it has a potential energy. So kinetic energy term is half mu square plus half k r square, that is the potential energy term. And like that manner, that non-rigid diatomic molecule has 7 terms under the kinetic energy. I will again explain. Non-rigid diatomic gas molecule, when it is moving, it has 3 types of motion. One is translation motion, second is rotational motion, and third is vibrating motion. Translation motion has a degree of freedom 3 because molecule can move along x, y or z axis. Rotational degree of freedom is 2 because when molecule is moving along in the 3 dimension, its motion is along one axis, while during that it will rotate about remaining 2 axes. Therefore, rotational degree of freedom is 2. And when it is rotating about that 2 axis, at that time it is vibrating about mean position. So, vibrational degree of freedom is also 2. So, 3 plus 2 plus 2. So, total degree of freedom is 7. Now, if degree of freedom is 7, then I can write down its kinetic energy. So, 3 terms for translation motion, 2 terms for rotational motion, and 2 terms for vibrational motion. So, vibrational motion consists of two energies. We have seen an oscillation, that is during SHM, when particle is performing SHM motion, it has a kinetic energy and it has a potential energy, and that is called as a vibrational mode. So, in vibrational mode, it consists of 2 terms. One is kinetic energy and second is the potential energy. So, during its motion, it will also vibrate along the x-axis. So, along the x-axis, so u is nothing but the velocity component along x-axis. That's why it is written half m u square plus half k r square. R is nothing but the position vector. Like in oscillation we have seen potential energy is equal to nothing but half k x square because particle is moving along x axis. अगर आपका particle यहाँ पे x axis पे move हो रहा है तो you can replace r by x and that is nothing but your potential energy. Clear? So this is all about your degree of freedom. Fine. So in this degree of freedom we have seen 5 important points. First point, when particle is moving along straight line, its degree of freedom is 1. When particle is moving along 2 dimension, its degree of freedom is 2. When particle is moving along 3 dimension, its degree of freedom is 3. But at that time condition is the molecules are the monoatomic molecule. Clear? When we are considering diatomic molecule, again that diatomic molecules are of 2 types. One is rigid, another is non-rigid. Non-rigid का तो आपके सामने है. For non-rigid diatomic molecule, degree of freedom is 7. 3 from translation, 2 from rotational, 2 from vibration. And if diatomic is a rigid, then rigid diatomic molecule has a 2 motion. One is translation, again second is rotational. So for translation motion, degree of freedom is 3. And for rotational motion, degree of freedom is 2. So like that manner, total degree of freedom for rigid diatomic molecule is 5. Got it? So this is about your degree of freedom. Getting? Any doubt? Clear? So this topic is very, very important for your MCQ question as well as for very short answer, that is for 1 mark. So for that purpose, observe this video carefully. 2-3 times go through this video. So you will be able to prepare for MCQ question as well as for very short answer type of question. Get it? Okay. So this lecture I will stop here. Next time we can go for the specific heat capacity. Fine. Thank you.